Welcome back for our second topic, and our pleasure to have Benjamin Viro and talk about the Graphical concept.
Okay, thank you. Thank you a lot for the invitation. I'm sorry I couldn't come in person today, but yeah, I had many drawings to prepare, so maybe it's for the best that I'm doing on the slides. Okay, so yeah, today I want to talk about some kind of graphical calculus, which will be about some graphs in 2D. So if you're familiar with string nets for Turaev Viro type of TQFT, this will be very similar, some twisted variant of this. And everything I'm going to talk about is from a paper that should appear on arXiv in, say, the next 2 weeks, but pretty soon. And this is all joint with William Stewart and Philippos Stylitis. Okay, and I've added some drawings to tease you about what's going to happen next. Okay, so maybe I'll start by recalling the kind of usual story for string nets for pivotal categories that will give us this Turaev Viro series. And somehow the point of view I want to take is that pivotal categories and pivotal structures are really a way to fix some problems that we naturally face when we're trying to do graphical calculus for rigid categories. And then these twisted pivotal structures that I will talk about are some, say, more general way to fix the same problem. And kind of, we didn't really invent this in some sense. We just asked the cobordism hypothesis for what the answer should be, and it spits out some, say, conjectural thing of what the answer should be, and then we just build the theory out of this conjectural answer. Okay, so this will kind of be the plan. Is the usual story, the kind of prediction by the cobordism hypothesis, and then the actual construction of this graphical calculus that is a bit different from the one we're used to. Okay, so I'll start with graphical calculus, and I'll say graphical calculi because there's very different notions of graphical calculus for different versions of input category that you start from. Okay, so maybe the most naive version is if I have a category, I will want to think of its objects as living on lines, and morphisms as being some kind of point defects on these lines. So f from x to y is some morphism in my category. And what this graphical calculus does for me somehow is that I have now a nice way to represent composition of morphisms. Okay, so if I have f, g, and h, this is somehow representing the composition of doing first f, then g, then h. So I'm reading from bottom to top. Not everyone does this, but I think it's the most standard way now. Okay. So this is somehow not too complex right now. If C is monoidal, then I kind of have two directions. Okay, my morphisms still going this way, but I also have my tensor product that I will represent in this direction. So for example, I can stack two objects next to each other, and this will represent x tensor y. Okay, and then I can represent morphisms that go from some tensor powers to some other tensor powers. Okay, so here my morphism goes from x tensor y to a tensor b tensor c. Okay, just get rid of that. I have some room. And now I can again represent different compositions and tensor products of morphism with my graphical calculus, and somehow this is now becoming very powerful. I can represent some things that would really be a pain to represent kind of as an expression. You see, if this is f, g, and h, somehow this is some different composition of f, g, and h where I have also inserted identities on the side, and I need to use a tensor product, so this will be quite a long expression. Okay. And what we'll really be interested in is in rigid categories. So on top of being monoidal, I have these evaluation morphisms. So I have X here, and here I have some kind of X dual, and this is some morphism from X dual tensor X to the unit that satisfies some zigzag identity with some co-evaluation morphism. Okay, and this kind of allows me to change the incoming direction of objects at coupons, and so we really like these. But there's some kind of problems here. Naturally, I would want now some strands living in the plane that can turn face up, face down. But there's some incoherence in this type of graphical calculus. For example, if I'm just drawing a circle labeled by X, here naturally the object that I will see here with this evaluation is this right dual of X. And here this co-evaluation is not the same as this one. If I look at this co-evaluation, what I will see here is kind of the left dual of X. Okay, so maybe let me do this a bit more clean. I just don't really close my circle. Here, really what I'm seeing here is this X right dual and it's this X left dual. And these two things are just not the same. So the circle doesn't really make sense. Okay, so the problem somehow is that if I have a strand facing down, I don't really know if I should interpret it as a right or as a left dual. Okay, so there's some problems with this graphical calculus for rigid categories. Okay, and so somehow, a theorem of Joyon-Street is that this all makes sense if I'm really imposing that I have some progressive direction. So my strands are always going up. I never have a strand going down. Okay, and then I can do any sort of diagram in the plane as long as all my strands are going up. So we will call these diagrams progressive. And here I have some evaluation of any kind of a drawing here into some morphism in my category, and this one is well defined. Okay, and what we would really like is to drop this progressive condition and to be able to draw circles and anything in the plane. Okay, and so the usual fix for this is a pivotal structure which identifies this left and right dual. Or in other words, identifies the double dual with the identity. Okay. I needed to do this in some coherent manner, so I want it to be natural and monoidal. I'll just drop this, but I have a natural way to identify this left and right dual, and so somehow all of the problems I was seeing before vanish, and I can interpret the strand going down as just being either the left or the right, and they're canonically isomorphic, and I'm going to be fine. And so again, a standard theorem of graphical calculus for pivotal categories is that now I can remove this progressive hypothesis. I can just draw any sort of diagram in the plane and have a well-defined evaluation functor into some Hom spaces. And now I've emphasized here, you can have some strands going down, and you just interpret these as some dual. Okay. Any questions so far? Yeah, and I also want to emphasize that I prepared a rather short talk, and I'm very happy there's plenty of questions. I can spend some time explaining any aspects of what's showing up here. So yeah, feel free to interrupt and to say disrupt the talk. Okay, so if there's no questions, I will continue in this story. Now that we have a good graphical calculus, the point is that we know how to build TQFTs. Okay, so if you start from an oriented surface and you give yourself a pivotal category, which I will also assume is linear over some field, then you can define these string net modules, which are some linear combinations of what are spanned by graphs, which are colored by objects of CE, so kind of locally look like the things we draw above. but which now live in my surface. And I consider these up to isotopy and something called skein relations. So these skein relations, I can only change my my graphs in some small region, so in some disk in my surface. Okay, and in this orange disk that I've drawn here, I can change the graph by anything which evaluates to the same thing. Okay, so in this disk, I have this evaluation functor that I introduced here. So any kind of diagram in this part of the surface, I can interpret as some morphism in C. Okay, and if these two different graphs represent the same morphisms, then I'll say that these two string nets are the same. Okay, and so these vector spaces are very nice because in some good cases, they extend to a TQFT. And this is going to be the Turaev Viro, a three-dimensional theory. Okay, so what I typically need is on top of pivotal, I need spherical, semi-simple, and finite. It turns out that semi-simple can be dropped, and this is a theory by Costantino, Gear, Patrimiron, and Viro. But I'll not talk about this too much, but it's secretly in the background. But so I have a way of assigning a linear map to every three-dimensional cobordism, and this whole thing becomes a TQFT. Okay? So what I'll focus on today is not so much the extension to 3D that we see here, but kind of making these foundations of what are the vector spaces that we assign to surfaces. In particular, on these vector spaces, I have an action of the mapping class group of my surface. Okay? So somehow they are coherent enough that any diffeomorphism of my surface will naturally act on these string net modules. Okay? So this will be one of the crucial difficulties for what's going to come next. Okay, so I have this kind of explicit description. If I start from a pivotal category, I can define some vector spaces by spanned by some diagrams drawn on my surface. And then I have some explicit formulas for how to extend it to dimension 3. Okay. And now I'd like to talk about some very different perspective on the same construction, well, conjecturally the same construction, which is given by the cobordism hypothesis. Okay. So this TQFT I build, it is secretly fully extended and is going to be classified by this very powerful algebraic tool, which is the cobordism hypothesis. Okay, so this slide is just a little interlude into higher algebra. It's not fully necessary for the rest of the talk, but somehow it was fully necessary for this project to arise. This is really the cobordism hypothesis that's going to suggest to us what type of structure should we look for. Okay, so I'll just do some definitions, some standard definitions. So a fully extended TQFT. So we'll say K is kind of the dimension of the bordisms I'm defined on, and N is kind of the the N category, the N for the N category in my target. And so somehow you should imagine that I would like an n-dimensional TQFT, but somehow this is only defined up to dimension k. Anyway, so such a fully extended TQFT is some symmetric monoidal functor from a category of bordisms to this target category S that I've chosen. In this category of bordisms, it has object 0 manifolds, so these are just points. Okay, I'll just do a little drawing on the side. Its morphisms are cobordisms of dimension 1. So for example, from 1 dot to 3 dot, I have this beautiful cobordism. And then its two morphisms will be some kind of surface cobordisms with corners. So for example, I have a cobordism from this one morphism to this other one morphism. Okay, and this is a bit difficult to draw, but you can kind of imagine what is the surface joining all of these things together. Okay, here I have a sheet. So you have some kind of funny surface with corners joining this one cobordism to this one cobordism. Okay, and so we kind of keep on playing this game, and we have higher bordisms with higher corners between all of these drawings. And eventually, when I reach K, I turn to diffeomorphisms and their isotopies. Okay, so I have such infinity K category of bordisms, and I map it to some, let's say, linear category S. Okay, and so the cobordism hypothesis classifies these fully extended TQFTs, actually only the frame ones in this first version, by so-called fully dualizable or K dualizable objects in my target category. Okay, and so just spelling this out for us, the natural target category to consider is some Morita category of monoidal categories and the bimodules. So my objects will be some kind of monoidal category, for example, the category C that I was considering above. And then morphisms will be some kind of bimodule categories, functors, and natural transformation. And so what this is saying is that if I want a fully extended TQFT valued in this kind of things, all I have to do really is to look at its value on the point, and this should be a K-dualizable object. Okay, so I really take some monoidal category, and I'm asking, well, if it's 2 dualizable, then I should get some things defined on surfaces. If it's 3 dualizable, then I should get something defined on 3 manifolds, and so on. And so it's a theorem of Douglas, Schneider, and Schomer-Priest that if my input category is rigid, then it is indeed 2 dualizable. And this kind of reminds us of these string nets modules that we can indeed define for some type of rigid categories. Okay, so we can indeed we could have guessed that, this implication, because we kind of know what to do on a surface from a rigid category, actually from a pivotal category. And if moreover my input category is finite and semi-simple, then it is actually 3 dualizable. Again, this is the type of thing that we need to define our Turaev Viro 3 manifold invariants. So again, somehow there's indeed, like this covariant hypothesis actually works. We can see this correspondence of when our object is dualizable and when we can actually define the invariants on surfaces and 3 manifolds. Okay, so far this all matches pretty well. But the type of things I want is not quite a frame theory, but an oriented theory. Okay, so here I didn't see my pivotal structures at all, and here I didn't see this sphericality condition, for example. And indeed, there is an oriented version of this cobordism hypothesis, which will now classify oriented theories, but by an object as before, together with an orientation structure, which is some kind of homotopy fixed point structure for some action of SO of K. And this is something that is very difficult to describe for us. This action of SO of K kind of uses the cobordism hypothesis in its definition. And so describing homotopy fixed point structures is something that's very difficult. But luckily, in our setting, again, Douglas, Schomer-Priest, and Schneider have given a conjectural description of what it means to endow a monoidal category, or say a rigid monoidal category, with an SO2 structure. So kind of what this whole slide is saying is that we can attack the same type of problems using the cobordism hypothesis. And given a rigid category, we can indeed do something on frame surfaces. And if you want to make this oriented, then there is a guess by Douglas, Schomer-Priest, and Schneider of what exactly is the data that you need. Okay, so what we're going to do next is take this data and try to actually build the TQFT, at least on surfaces. Okay. Any questions again? Okay, so before we start using this data that the SS described, I want to talk a little bit about foliated surface and what is the graphical calculus that we have just for rigid categories without doing any extra data. What can we do for rigid categories? Okay, and so a little reminder, what we needed without a pivotal structure is that our strands in our graphical calculus are all progressive. So I need a progressive direction, and I want all my strands to go a little bit along this direction and never turn back. Okay? And another way I can describe this is to draw the lines which are not progressive, which are horizontal for this direction, and say that my graph must always be transverse to these lines. They can never be tangent to the line. They cannot turn back. Okay, so I have a graphical calculus for progressive graphs inside anything of dimension 2, which has this notion of progressive direction or which has a foliation like this. And one obvious problem is that for any surface which is not the 2 torus, for any closed surface which is not the 2 torus, then I cannot find any such notion of progressive direction. I cannot endow any surface with a foliation without any singularities. And so you can, for example, try to visualize this on the 2 sphere. If you start from the South Pole and here just do your standard foliation, then kind of what you're going to see near the North Pole is some drawing like this. And this you can convince yourself there's no way of extending into a smooth foliation. Is this somehow the same statement as the fact there's no non-vanishing vector field on a surface, which is not the torus? And this you know because it has not zero Euler characteristic. Okay, so this notion of progressive graphs was very nice, but somehow is not enough for us, and we cannot do our surfaces with that. And so our solution will be to do this kind of almost everywhere, but to allow some type of singularities. And so what we're going to do is use a Morse function on our surface. Okay? Morse functions always exist, and we have a pretty good control as to what they look like. And a Morse function induces some foliation on your surface by just taking the pre-image of every level. If I have a level here, I will have a pre-image here, and so on. And this will have some singularities at the critical points of my Morse function. Okay, and again, we understand these critical points quite well. And so for a surface, there will be only 3 types of singularities. Index 0, so a local minimum for f, which is what's happening near here, and so a bunch of concentric circles and a singular point in the middle. Index 2 is kind of the same for a maximum of my Morse function. And kind of they differ by which direction is the progressive direction. Okay, so this is kind of the up direction in R. This one is I want everything to go out, and this one I want everything to go in. Okay. And then somehow the most interesting one is this index 1 critical point where I have a saddle. Okay, and just to convince you that now I've solved this kind of issue I had before, I can indeed draw this type of foliation with some singularities on the 2 sphere. Okay, so this is nice, but I know what to do on a smooth foliation like this. I have a graphical calculus in my category for this type of things, but right now I have no idea what to do on a foliation with singularities. What are string nets in this type of surfaces? So this is exactly what we're going to try to solve now. So first I will define this notion that Douglas, Schoenmapris, and Snyder pointed out, which we called a twisted pivotal structure. So now I start from an object of my category, which is invertible. And I will define a notion of alpha twisted pivotal structure, which is, so remember, a pivotal structure will be an isomorphism between the double dual and the identity. And I somehow twist this or conjugate this with alpha. And so I have an isomorphism between double dual tensor alpha with alpha tensor the identity. Okay. Again, this should be natural and respect the monoidal structure. And moreover, I'm going to ask an extra condition that so from this structure, I can define a twist on alpha. I can kind of make alpha cross itself and do a twist like this. And I will ask that this twist is trivial. Okay. And so this is exactly what we expect to be an SO2 structure on my monoidal category C. Okay, and now I can define what string nets should be on any of the drawings I had above. What I'm going to insist is that there's always an alpha colored strand that is emitted at the singular point. So either it's an alpha strand that's emitted, or it's an alpha inverse strand that is emitted. So there's some type of rule. For index 0 and 2, I want to create an alpha. So either create an alpha or absorb an alpha inverse. Okay, so but this adds an alpha to the whole thing. And for index 1, I want to kill an alpha. So either absorb an alpha or emit an alpha inverse. Okay, and so now I have a notion of twisted string net module, which are spanned by, again, graphs in my surface, but which are progressive for this, this foliation I have. So progressive, say, away from the singularities, and just at the singularities, they must have this standard form. And I will quotient this by the usual relations, so isotopy and skein relations, and also some new ones, some sliding relations. Okay, so you should imagine that a strand that is on this side, I should be able to push to be on this side, because these singular points are not punctures. I can still slide strands above it, but they will interact with alpha. Okay, and so I have some little drawings here. If you have a strand that's on this side, you can push it on this side, but you will need to use your twisted pivotal structure. And actually, so in order to make your strands transverse everywhere, you need to introduce coupons every now and then. And so naturally, what is going to come out is some kind of dual for your object. And depending on which side you're using, it will be a different dual that shows up. So here it is very essential that my twisted pivotal structure actually is killing a double dual for me. Okay, so I have this drawing for index 0 and index 1, and the one for index 2 is very similar. I also have a little relation that tells me I can change which way I come into a saddle. Okay, and so the claim is that this is a reasonable definition for what to do on a surface. Okay, and so there's many things we need to argue for why this is reasonable. So one thing that we do is that we compute this thing on some small examples of surfaces and show that the answer is kind of what you should expect, and in particular not 0 all the time. But somehow for us, what is the main motivation is to so remember, with usual pivotal structures, we don't need to talk about foliations at all. We can just talk about oriented surfaces. And this is really what we're trying to do here, okay, is to also talk about oriented surfaces. So somehow these foliations are an artifact when we're computing the actual vector spaces, but the vector spaces should be assigned to oriented surfaces. And so this is the main result that we prove, is that this notion of twisted string nets that really use a Morse function and a singular foliations, they actually form an oriented theory, an oriented TQFT, which is only defined in dimension 1 and 2 and not in dimension 3. But you should expect that in good cases, it will extend to dimension 3. And so kind of the very important part is this oriented. A priori, we've defined this on some category of bodisms where my surfaces are equipped with a foliation, with singularities, or say with a Morse function. And here we claim that somehow this was not really necessary. So if you pick a surface and you pick two different Morse functions on the surface, then we have a canonical isomorphism between the two vector spaces. And in the same spirit, the mapping class group, so diffeomorphisms of my surface, will act on these twisted string net modules. Again, this is very not obvious. A priori, I should only allow mapping classes that send the foliation to the foliation. Okay? If a mapping class sends the foliation to the foliation, is very clear how it will act on the string net modules. The image of a progressive graph will be a progressive graph, and I'm going to be okay. But for a general diffeomorphism, it's really not clear how this will act on the string net module. Okay, and so the core idea of the proof is to understand what it means to change Morse functions. Okay, and this is surf theory. So if I have a generic path between my two Morse functions, then somehow generically this will only have two types of interesting singularities: these cups and these crossings. Okay, so I've shown you what these do on the foliation. Okay, so the point is that these are some kind of diffeomorphisms of surfaces. Here, really, it's the identity diffeomorphism from the square to the square, which do not preserve the foliation. Okay, so here they do not preserve the Morse function, if you want. So what this is saying is that string net modules on this foliated surface should be the same as string net module on this one. So I have to provide an isomorphism between these two string net modules because, well, these are the same oriented surface, they just have different foliations on them. And the way we're going to do this is really, well, pictorial. Is we can isotope our skein to be kind of as far away from this region as possible. But okay, we must have some skein still here because we insist that there's some alpha strand coming in here. Actually, I should have reversed the orientation. And so if you have such a skein that you've kind of pushed everything far away except the alpha strands that are imposed, well, the natural image for such a thing would be something like this. Okay, so you can think of this cusp as joining these two critical points and they vanish together. And so we kind of just do this natural thing at the level of string nets. And what we claim is that this is a well-defined isomorphism between the two string net modules. Okay, so there's some topology involved into actually proving that. But we have an isomorphism between these two vector spaces. And similarly, the crossing, so the crossing is maybe not so clear in this drawing, but it's really only happening in these two regions. Okay? Everything away from these two regions is exactly the same on both sides. And what I'm doing is squishing some saddles. Okay? But it does have an influence. Here you see like this type of path here, which there's one leaf going from this side to this side in this direction, and it's very different on the other side. If I try to do the same, I would be very transverse. Okay. So these two things are very different as foliated surfaces, okay? But somehow the difference is happening very locally near the saddles. And again, for string nets, locally near the saddles, I can just make sure I'm of the form of like one alpha strand, say leaving. And if you have an alpha strand leaving exactly perpendicularly, you can just keep it here. Okay. So again, you should check that there's some check into seeing that this is a well-defined isomorphism between these two modules, but somehow the core idea of what is happening is pretty simple. Okay, so we define these isomorphisms between different twisted string net modules for different foliated surfaces that correspond to the same oriented surface, but just with different foliations. And then one thing that we have to check again is that this does not depend. So we build the isomorphism that we wanted here between the two string net modules, given this generic path. But again, we have to check that this will not depend on the choice of path between our two Morse functions. Okay, so this is the next level of surf theory, is understanding what is the generic path between two passes of Morse functions. Okay, and again, there is some singularity theory of what type of singularities can you see, and we just have to check a certain number of relations that are diffeomorphisms, our isomorphism of vector spaces respect these extra relations. Okay, so this is kind of the technical heart of the paper is showing that the theory that we've defined, which maybe seems a little bit ad hoc with many relations that we've just introduced, and that a priori depends a lot on this choice of Morse function, actually is really a theory of oriented surfaces. Okay, great. So this is our main result. I just mentioned some examples. So these are taken from a paper of Sebastian Harbig, who makes a bunch of computations with these and kind of study pivotal structures and what he calls quasi-pivotal structures on this kind of half algebras. So I've written here all the generators and relations just so you can take a look. The point is that we have a good way of generating many half algebras from a number n, which is the order of the root of unity that we're looking at, and then a bunch of coefficients in Z mod n, which will decide on the Q commutativity of our generators and somehow the order of our generators. And so the claim is that we can study pivotal structures and twisted pivotal structures for all of these examples, and we can really see somehow what is the difference between these two notions. In particular, we can just compute and check that we can find examples of a rigid category of modules over this half algebras, which admit no pivotal structures, but do admit some twisted pivotal structures. Okay. So somehow we can reach more examples. And one important motivation for us, which is a bit hard to state here because I really try to drop all the non-semi-simple problems. But there's some cases of categories which are so-called non-unimodular, for which we know that the standard techniques cannot give any three manifold invariants. But with our twisted pivotal structures, we can show that actually the usual obstruction for obtaining three manifold invariant vanishes. So a priori, we expect that we have somehow partially solved this problem and that we can define three manifold invariants from these so-called non-unimodular categories. Okay. So this may be to convince you that there's some interesting examples to look at. This is really the early stages. Okay. I have an extra slide with missing definition, but I'll come back to this if there's some questions. But I'll stop here. Thank you for your attention.
Can I ask something?
I can hear that there's someone talking, but I didn't hear the question.
Okay. Can you? It's about the non-semi-simple thing you mentioned.
Oh yeah.
So you're saying the non. So I'm guessing the half algebra that you wrote is not unimodular. So if so then it means so in the unimodular case you can specify the traces.
Sorry, I really don't hear you that well. Can you try speaking a bit louder or closer to the mic?
Can you explain how this twisted pivotal structure would provide you some kind of modify the choice, fix the problem of the non-semi-simple?
Yeah, okay, yeah, I can talk about this a little bit. So let's create a new slide. Okay, so one thing I haven't talked about, but which is somehow standard in the literature, is if your input category C is non-semi-simple, then really you should forget about C and work with projective objects. And so whenever I define string net modules, I should insist that I'm coloring everything with projective objects. And I should also insist that there's at least one projective object everywhere. Okay? So this is very important when you're looking at the two-sphere, which drew it in gray. If I'm looking at the two-sphere, okay, in the usual setting, I have some complicated string net on my two-sphere. I can make sure it avoids the point at infinity and just think of it as something on the two disk. And then I can evaluate the whole thing to some endomorphism of one. Okay, and so you can see that the two spheres at most one-dimensional, and it's one-dimensional if it's the category is spherical. But in this, so this is usual. And this is not semi-simple. In this not semi-simple case, I will still have my two-sphere. I can still push everything to happen in a small disk in the two-sphere, but I will insist that there's some projective object somewhere. And when I do my skein relations, I will insist that somehow I leave a skein, a projective object away from the relation. So I cannot evaluate the whole thing to a scalar times the empty set, and I must always have some projective living around. And so what you end up with is somehow you will always have some projective cover of the unit surviving, and this guy has a unique. It comes with a map to the unit, and what you're asking in general is, does there exist a map from the unit to this P1? Okay, and home, and this is exactly so. It exists. Sorry. This is the same thing as unimodularity. Okay, so this is the usual pivotal case. Let me draw well, not non-pivotal, but twisted pivotal. Now my two-sphere, it's a more complicated object, right? I have these things with a singular point here and here, okay? And so when I try to do the same type of arguments, instead of having a map epsilon to the unit here and a map eta from the unit, I will have my P1 again. I must have some projective somewhere, but somehow this map will map to, let me check. So this one will emit an alpha, and this one will absorb an alpha inverse. Okay, so this is not P1 anymore. Well, if you turn things around, you will get some, like, you turn your alpha inverse around, you will get something here. You have some alpha squared. Sorry. Going into some P1, going to the unit. Okay, so the fact that the two sphere has Euler characteristic 2 is telling you that you should add two alphas. How you will have two critical points which emit an alpha. Okay? And so you're shifting your whole twisted string net modules by this alpha squared. Okay? And now if alpha squared maps to if you have maps from alpha squared to P1, then this vector space will be not zero. So if there exists a not zero map. So, okay, I don't know if that answers your question. This is somehow how this gets solved is that you don't insist that this is a map from the unit to a projective to the unit, but it's actually a map from alpha squared to a projective to the unit. And so if you choose alpha correctly, then this kind of things will exist.
Yeah, thank you.
Cool.
Another question. So let's find the experiment.